As our last application of integration, we're going to compute a moment of inertia. Now in physics, the moment of inertia of an object basically tells how hard it is to twist it around the origin. So if you have something with mass m that's a distance r from the origin, then the moment of inertia is defined to be m times the distance squared. As I said, this tells you how hard it is to spin something around the origin. If you have a weight that's very close to the origin, it's easy to spin. If you take the same weight and move it twice as far away, it becomes much harder to spin. That's why you see ice skaters pull their arms in when they're trying to do a fast spin. The farther their arms are out, the bigger the moment of inertia, the harder it is to spin. So, suppose we have a bar, has a length 1 meter, and it has a mass 1 kilogram, and we're going to think of it as a thin bar. We don't worry about the y and z coordinates, just the x coordinate. And it's a uniform bar. It's not any heavier at one end or the other end. It's a long bar, and we want to ask what's its moment of inertia. How hard is it to spin this bar around the origin? Well, we know what the mass is, but what's the radius? Do we mean the radius at this part of the bar where the distance is very small, or the radius at this part of the bar where the distance is very large? So we're going to apply the same technique we use for anything that's variable. We're going to break it up into lots of little pieces, each of which is at pretty much a fixed distance to the origin. So, as always, we take out our saw and we cut our bar into n pieces, and these pieces are supposed to all be the same, but my artistic ability is somewhat lacking. So, as usual, we call this x0, 1 is xn, and we cut at points x1, x2, x3, and so on. Each piece has thickness delta x, which is 1 minus 0 over n, so that's 1 over n. And we have to figure out what is the moment of inertia of each piece. Well, the moment of inertia of each piece is the mass of each piece times the distance squared. So the mass of each piece you get by proportions. Each piece is a fraction delta x over 1 of the whole. And the whole thing is 1 kilogram. So the mass of each piece is delta x kilograms if we're measuring distance in meters and weight in kilograms. And then the distance of each piece, well, there it's not exactly the constant. If you have talking about this piece right here, you might mean the nearest distance or the farthest distance, or you might take a distance, a point in the middle. Call that point in the middle xi star if this is the ith piece. Xi star is somewhere between xi minus 1 and xi. So the moment of inertia of each piece is going to be approximately, it's approximately because we don't have the distance exactly right, it's approximately the mass of that piece times the distance squared, because that's the definition of moment of inertia. The moment of inertia is the mass times the distance squared. As always, we want to get the total moment of inertia, MOI for moment of inertia, is going to be the sum of those contributions, xi star squared times delta x, and the total moment of inertia. To get it exactly right, we take a limit. The limit as you take more and more and more pieces of the sum over the pieces of xi star squared times delta x. And by definition, That is the integral from 0 to 1 of x squared dx. So we've seen the same integral come up 4 times. We saw it as the area under a parabola. We saw it as a distance traveled. We saw it as a volume. We saw it as a moment of inertia. Whenever you see an integral like that, don't just think area under the curve. Think this integral means the limit of this sum. This sum might have come about from figuring out volumes or moments of inertia or areas or distances. Doesn't matter what kind of problem it is. Whenever you've got a problem involving a bulk quantity, slice and dice. Estimate the pieces, add the pieces, take a limit, and you'll always get an integral. Integrals are magic. They're one of the most powerful ideas of calculus, and that's why I call it the fourth pillar of calculus.